I am starting by showing you a video that shows what the problem is, what the motivation is. So,
ultrasound is a very useful and powerful imaging technology. It has to be used in many clinical situations and very emergency situations. Ultrasound technology is very convenient technology because it don't need huge and heavy machines like MR. You have very small and user-friendly ultrasound machines, maybe so small as your iPhone. The main problem with ultrasound that it has to be performed by trained people.
There are many situations in which ultrasound imaging is useful, but there is no specialist or no hospital nearby. Imagine first of all rescue operations, an ambulance, a helicopter, maybe even on a battlefield. Also, imagine rural areas where the nearest hospital may be hundreds of kilometers away, and maybe even in developing countries, thousands of kilometers away. Looking a bit further ahead, nowadays, your family doctor, whenever an ultrasound scan is needed, will tell you to go to the hospital to get it taken, and then you will need to queue up, and overall this will entail a lot of costs for the overall healthcare environment. What if your family doctor could take the scan directly in the cabinet and then upload it to the hospital for analysis?
Telesonography is a huge problem because the people that is performing ultrasound has to be the people that is interpreting ultrasound. That means there is a huge distance between the possibility to bring the technology and the possibility to understand what you are doing.
In the Ultrasound2Go project, we are designing a 3D imager. That is very significant because it means that instead of acquiring a 2D image of a thin slice of the body, which is maybe not what precisely we need to detect a tumor or to detect some anatomical feature, we actually image volumes, pyramids. These pyramids are large enough that even an inexperienced operator can put the probe on a given location of the body, maybe according to a leaflet or a tutorial video, and acquire the volume of interest. Then this volume can be uploaded to the hospital for analysis. We are optimizing the digital electronics, the software, and the algorithms to design an imager that is extremely high quality, yet low power and low cost. We want to make it small and portable enough to be usable on the field, yet cheap enough so that every family doctor could have one in the cabinet. This is how it works. On the field, an inexperienced operator acquires a 3D volume. If needed, a video tutorial or a poster can help identifying where the scan should be taken depending on the type of suspected diagnosis. First of all, we put the probe in a reference position and mark it by pushing a button. Then we sweep the probe where needed. Thanks to accelerometers, the probe tracks its own relative position. By pressing on another button, a volume is acquired, tagged with the position it was taken at, and uploaded to a hospital.
We are working here with an ultrasound simulator. It is composed from a puppet with electronic detectors, a fake ultrasound probe, a computer, and a screen.
To allow the radiologist to browse the acquired volumes in a way that is familiar, we can use this existing technology. The puppet and the fake ultrasound probe include positioning technology that precisely detects the location and orientation of the probe on the simulated patient. In this industrial product, the technology is used to display simulated images for training purposes. We propose to display instead the volumes acquired on the remote patient. So, by sweeping the probe, we will be able to locate precisely his or her anatomy. For example, we can identify here an internal hemorrhage, and we can now communicate the diagnosis back.
Let me say that it's a great thing to start a talk and give a movie and realize that the actors are actually present in the audience. Even the patient is here in the audience. And let me add a couple of things just to be clear is the example with the probe on the patient is a proof of concept. And we do not typically do experiments on graduate students. But I would like to thank actually Giovanni for helping us doing the video because I think that conveys the idea of what we want to realize. So we've seen a vision which is extremely important for medicine today and what is needed from an engineering standpoint. Well, first we need to have portable, inexpensive, and low-power scanner. The scanner has to be 3D because you want to acquire volumes rather than images. This basically reduces the threshold capability of the operator. You can use inexperienced operators to do to take a volume and have this volume then analyzed remotely by an expert. So this actually helps a lot. The only other way of doing that is to have a robot manipulating the probe. This actually is part of a project of the European Space Agency in which they envision the fact that there could be a remotely controlled robot who would manipulate the probe. This just because of this important fact that the probe movement and positioning is key in order to understand the images. And then, of course, we want to have good enough imaging quality for the applications where we want to use ultrasound. Also, transmitting images, we have to have a protocol to tag and remotely visualizes the images themselves. Now, in this domain, there are already several products, and it's important to know what's around to understand what we want to do. For example, there are professional 3D scanners, but they are typically expensive, they are bulky, and more than that, they consume more than 500 watts. So these machines are good for hospitals. They could be good also for doctors' offices, but these are not portable machines. So our objective is really to get into the scale from 1 to 10 watts. So you have a device that can be used on an ambulance, on a fireman truck. It can be put, for example, in a telephone cabin, made available to the general public. Now, there are several efforts for having mobile ultrasound. For example, ST Microelectronics has announced about 2 or 3 weeks ago the US 304 model, which is mobile, but that enables only 2D ultrasound. Philips also has a very simple system that consists of a head that can be just hooked into a portable display, but again, that's only for 2D. The first attempt to do a miniaturized 3D has been done by BK Ultrasonic, and it's a device that would help to do intravenous shots, and it's a way to visualize veins or arteries. But this type of devices will not really render a volume, but will give a cross-section and will just be geared toward having more precision when you insert a needle. So what we want to do is we want to develop a system that has the capability of a large 3D ultrasound system within a very limited size and power budget constraint. What's the progress on this project? Well, we've been working on advanced modeling of the acquisition process. This work has been mainly done in MATLAB. We've been looking at various algorithms to manipulate the images. We have co-designed a new 3D probe, transducer and circuit. This is work done together with Fraunhofer in Germany. We have realized a digital beamforming circuit on a FPGA platform, and in parallel we have studied how we would realize beamforming on a parallel computer. It's a Calray machine. And eventually we have studied improved algorithms for using compressed sensing that will allow us to reduce the cables, reduce the analog electronics in doing ultrasound. So starting from the matrix array, the probe. The picture that you see here, it's also very recent. It came to us in about 10 days ago, I think. It's been done at Fraunhofer. It's 32 by 34. That is 1024 elements. And what we've done in the project, and this was done in the Zurich lab, it's the construction of miniaturized electronics that actually can link directly to the probe. The final assembly is imminent since now we have the probe. This picture actually shows what is the setup, and if you go to the demo side, you can see it from real. The important thing is that this has reduced the volume as well as the cross-section of the hardware as compared to previous hardware, so we can think of these analog electronics together with the probe to fit into a case that can be handheld, and that's extremely important. Now, if you look at the global picture, what we have in mind today is that we have the blue part, which is the probe, then there is this analog setup, and then there is the backend. The backend now is done by the DFAS, which is a machine done at Fraunhofer, where there is an analog front end and a digital back end that does the beamforming. Now, we have worked out on several beamforming alternatives, one on FPGA board, the other one on the Calray machine, and the question is how we're going to try all these things together. So we have two alternatives here. It's one actually to get just data on memory from the DFAS machine and port it over offline to our boards. And the other one is to acquire a machine like that. We just got the news we got half of the grant in order to get the machine. Now we're working on the remaining half of the grant to get a machine like this, and then we'll be able to connect directly our FPGA boards to the analog backend. So this is the board, the development board. Again, you're welcome to go and see the demo outside. It's a Kintex UltraScale FPGA board that has its own interface to the outside world. What is the highlights of what we have done is basically we have a 32 times 32 channel acquisition system that actually can deal with a fairly large configurable volume. We are talking about 2.5 megavoxel per frame and 1 insonification per frame. So we have a system that can do beamforming, which is more performing than what is in typically other machines. And the big news is that this can operate at 4 watts, which is actually within our specs. Now, the future for that, we are looking at building a different system which is lighter in the terms of the size of the probe and the analog circuits, so that all the analog circuits can be integrated, including the analog to digital conversion, into the head that is unheld, and therefore replace the cable. These cables are typically a pain, they are very heavy, they are very expensive, but we can replace them then with an optical digital high-speed cable that will link to our backend on an FPGA. Now, at the same time, we have had development on a multiprocessor. This is a Calray machine, and this is a 16 by 16 cluster of 16 processors. And so most of the work here has been done into mapping the various functions to the processor and in developing a tool chain that will acquire correct and safe data acquisition on this multiprocessor. In order to do that, there are many computations of worst-case execution time analysis, and so this design flow, which I don't have the time to explain here, but you will see that at the poster, shows actually how the various tasks of mapping software to the processor can be done in a way which is safe, coming to a static schedule that then can be also optimized at runtime. With this, we have done 2 sets of experiments, and the bottom line of these experiments are the following, that in one case, if you work on a single processor, you take 30 seconds to do a thread, and when you go to a multiprocessor, you will get half a second, so it's a speed up of a factor of 60. If you look at the right part of the picture where we have a different type of setup, we can reduce 13 minutes to 14 seconds. Again, it's a speed up of about 60, so it's significant. Now, since I see the chair that is getting nervous, I get to the last slides. I want to show you what has been done with compressed sensing. Compressed sensing is a technique by which you do an undersampling of the image and then you reconstruct the image and you get good quality. It's extremely important because you reduce power, you reduce cabling, you reduce computational effort to do that. And this is shown by the following pictures of a carotid. You will see a reference image which has been acquired with 128 elements, and here you have a contrast ratio of minus 31 dB. You can see that the picture on the left is quite clear. The picture in the middle is what we can do with compressed sensing. Here you would use only 32 elements, but you can still reconstruct an image with very, very good contrast at 31 dB. And on the right, you will see what you would get with a 32 element system where you don't actually have the compressed sensing, and you see that there's a lot of noise which is encircled there, and that's actually an image that doesn't have enough of good contrast. So important point here is that we can have a significant data reduction down to 75%, significant decrease of memory footprint, again, 75% reduction, still by keeping the good image quality. So, in summary, we have developed a front-end ultrasound system in collaboration with Fraunhofer. We have developed a board that does the digital beamforming. We have also a tool flow for mapping a beamformer onto a parallel Cal-Ray machine. We have designed compressed sensing algorithms for reducing the system size and power while still keeping the image quality. And we had quite a bit of interaction with the doctors at SCHUV. I'd like to thank the following labs that have been involved with this project at the EPFL, at Zurich, at SCHUV, and again, I would like to thank you for your attention.
Thank you. So we have a little time for questions. Are there any questions in the audience? Yeah, the audience is very quiet today, so maybe I'll start.
Only the chair was very...
Trying to cut down on time, right? We're trying to keep time. But Nani, when this is going to see the light in the medical practice? I mean, that every physician around the corner will get this kind of device.
Well, to build a open software system, it's complicated because you have to go from the probe down to the circuits. I think that what we can achieve in this Nanotera project is a proof of concept that we can have the probe, we can have the circuitry, we can have the algorithms, we can have the various components. I think this is a project that should go on. I think there's really the possibility of building a system where you will have various advantages. One is the portability. The second is that the engineers and the doctor will own the system, so you can put software add-ons, you can do things that you cannot typically do on a system that you buy, that actually comes as close. And I remember Dr. Muri told us, you know, the biggest thing that we can do in the short term is to enable general practitioners to have a system like this. Because general practitioners typically do not know how to operate an ultrasound or cannot do it, and so they will refer the patient to a radiologist. And this will take time, and you will have to go various iterations. Well, if you can do an ultrasound scan in a doctor's office, that will be already a major improvement. Then from there, you can think of ambulance, you can think of war situation, you can think of the Jungfrau Joch and all that. But that's, that will follow.
Yeah, that's the challenge, and hopefully, but you never named the time. Of course, it's very difficult.
The more money is given to us, the shorter will be the time to deliver it.
Quite simple algorithm, right? The times amount of money. Are there any questions from the audience? Well, if not, just one more very short one. That is, what about the wireless communication between the two parts? Because you said, well, we're going to have a thin cable, but maybe you don't need a cable.
You're kidding? No. Okay, so somebody who wants to do this work, the first thing he or she has to do is to go to a good hospital like SCHUV and see what is there. You go there, you see this machine, because there are these 3D machines that are great, they do all these images. But the thing that shocks you is the cable. First, when you handle the cable, everybody watches you, because if you drop the cable and you just hard the connector, that's 10,000 francs or more than that. The cable is a huge piece of engineering. It's a huge bottleneck, because the amount of information, you're talking about 2.5 giga sample.
Yeah,
Or
but
that's
you
per
already
second.
moved it. You're already moving it to another
No,
part.
no, no,
right?
no. But that is a huge amount of information that you're doing. So in order to avoid that, you have to bring in intelligence next to the probe. But it also means to build electronics that can be extremely compact next to the probe, and that cannot really heat too much, because you don't want to have a hot object that you put on a patient. So that's the key thing. So I think that achieving probably digital transmission of samples that are compressed over an optical cable is doable, but going farther than that, it's more complicated, because you want to go from the head to the beamformer.
Yes.
From the beamformer down the line, it's easy. Then,
Right,
then it's
right,
then the
yeah.
back end you can use
Well,
standard things.
that's the part I was
but there
talking
is the
about.
part where you really have this very high data rate.
Sure. Okay, thank you very much. If audience is quiet, hopefully for the second talk it will be different. Well, thank you. Thank you, Nani.